Hello friends, I am Professor Dgt going to take your second lecture in PH 6503, unit number 1, electromagnetics. This is going to be the chapter number 2. We have already learned about the Maxwell's equations. What are the Maxwell's equations? Which are governing the electricity and magnetism. These four important Maxwell's relations are like this. Divergence of D is equal to rho, divergence of B is equal to 0, curl of E is equal to minus del V upon del T, and curl of H is equal to J plus del capital D upon dt. This displacement current density was introduced by Maxwell, hence all these laws are known as Maxwell's equations now. Using this Maxwell's equation, we are going to study the next point, that is 5.9, decay of free charges. One of the important deductions that can be made from Maxwell's equation is regarding the decay of free charges. We will be utilizing here the equation number 4, that is the modified Ampere's law. Curl of H is equal to J plus del capital D upon dt. J is nothing but conduction current density and del D upon del T is nothing but displacement current density. This term was introduced by Maxwell. Now, we can replace J by sigma E because conduction current density is related with the electric field inside a conductor with sigma E. See here, the sigma is nothing but the conductivity of the medium, and D is the displacement electric field which is related with the electric field with the equation that vector D is equal to epsilon vector E. So, D can be substituted as epsilon vector E. Here sigma, which is the conductivity of a particular medium or conductor, and epsilon is the permittivity of that conductor, or hence both these are constant. Sigma and epsilon are constant. So, they can be taken outside. You can see that here in a differentiation. Now, on these equations, if we apply the divergence, that means we are applying a del both the sides, but with the dot product of these vectors. That means del dot curl of H, that is equal to sigma divergence of E plus epsilon del T of divergence of E, that is equal to, we can substitute what is the divergence of E is equal to rho upon epsilon 0. Rho is nothing but volume charge density, charge for unit volume. So, divergence of E is going to be replaced by rho, or here inside this conductor rho upon epsilon will be there. So, we can replace sigma into divergence of E is equal to rho upon epsilon plus divergence of E is equal to rho upon epsilon. That epsilon will be cut with this one. So, it is written as del rho upon del T. This is a first order differential equations, and we can get the solutions of this differential equation by taking the integration of this one. So, if we integrate, because rho is a function of time, rho is changing with respect to time, so we can integrate with respect to time, and hence we will get this integration is equal to rho is equal to rho 0 e raised to minus t upon tau. Rho 0 is nothing but the volume charge density at t is equal to 0. Initial charge density will be there, which is decaying. So, that is called the charge which is going to be decay. Here tau is known as relaxation time, and this is called and is known as the relaxation time, and tau is equal to epsilon upon sigma. From this integration we can obtain the value of tau. Epsilon is the permittivity of the conductor and sigma is the conductivity of given conductor. The relation shows that any original distribution of the charge decaying exponentially at the rate which is independent of any other electromagnetic disturbances that may be taking place. So, a conductor which is carrying this charge, that charge is going to be decaying into free space. And how it is going to be decaying? So, initially the charge density was rho 0, then at any instant of time charge density can be given by this formula. Charge density rho is a function of time at any instant of time is given by rho 0 e raised to minus t upon tau, and this is independent of any other electromagnetic disturbance that may be taking place. Thus, any excess of the charge density in the interior of the copper conductor, which is given the sigma is equal to 58 into 10 raised to 6 ohm meter raised to inverse. Why it is inverse? Because ohm meter is a unit for resistivity and conductivity is inverse of the resistivity. That's why this unit is written as ohm meter inverse. Will disappear with the time constant. So we can write the time constant tau is equal to epsilon 0 upon sigma. The value of epsilon 0 is the permittivity of a free space. That value is equal to 8.85 into 10 raised to minus 12 upon sigma, which is a conductivity of a copper conductor, that is equal to 58 into 10 raised to 6. This we can write 5.8 into 10 raised to 7. 8.85 is approximately 9 and 5.8 is approximately 6. So this denominator and numerator we can write like 9 upon 6, that comes out to be approximately 1.5, and this 10 raised to 7 will come into the numerator. That means this multiply power is going to be 10 raised to minus 19 second. So relaxation time tau is in the order of 10 raised to minus 19 second. At this speed, the charge is going to be decaying from conductor. It means that it is decaying very fast. So this is related with the decay of free charge. Next topic which we are going to study is 5.10, potential of electromagnetic fields. What is the potentials? You have already studied the potential. Amount of work done to move a charge from one particular points to another particular points, that called the potential difference. That is Vb upon Vb minus Vba. Or you can say that 1 coulomb charge bringing from infinite distance to a distance d, the amount of work done is called a potential with respect to infinite distance. This is the way the potential was defined. Potential is a scalar quantity. Electric field is a vector quantity. And we have studied that if you want to study electricity and magnetism, what is important? In a given space, how the electric field and a magnetic field is distributed in that given region of the space. That means E is a function of R and T, B is a function of R and T, that we should know. That description should be known. So, for complete description of the electromagnetic field can be obtained by solving the Maxwell's equations. Maxwell's equation represents that how the electric and magnetic fields in that volume or in a given volume is distributed and how they affect on the electric charges. So this complete description can be obtained by solving 4 Maxwell's equations, and the process becomes simple if the equations are written in a suitable forms. These equations are in a differential forms, so it is easy to solve them. But if we reduce the number of equations, then it is more convenient for us to understand the electromagnetic field in a given region. Our complete description of the electromagnetic field in a given region can be obtained by solving this Maxwell's equations. And if these equations we can reduce to less number of equations by introducing new quantity which is called electromagnetic potentials. Electromagnetic potential we already introduced in static case. So if there is a static electric field is there, then the relations between the static electric field and potential was given by this equation E is equal to minus grade phi, or negative gradient of potential will result in electric field. Potential is a scalar quantity. Calculations of the potential and finding of the potential is easier compared to the vector quantity electric field. And once the potential is found out, we can apply del over here, and gradient of a potential, that means scalar, is always a vector, and that way we can obtain the electric field. So this is the things we have utilized in electrostatic condition. Similarly, the magnetic field can be obtained by B is equal to curl of vector A. Vector A is nothing but vector potential. Phi is a scalar potential. So this was introduced in electrostatic as well as in magnetostatic. Now the same thing we are going to take for time varying electric and magnetic field. So let us consider this potential in electromagnetic fields when the electric and magnetic fields are time varying. To understand this, we start with the Maxwell's equations. Maxwell's equation number 2, that is divergence of B is equal to 0, and Maxwell's equation number 3, that is curl of E is equal to minus del B upon del T. So these equation 2 and 3 are known as homogeneous equations because they doesn't contain charge or currents. That's why they are known as a homogeneous equations. Equation 1, divergence of D is equal to rho, which contains the charge density. Similarly, the fourth equation, curl of H, that is equal to J plus del D upon del T, that also contains the current density J, and hence this equation number 1 and equation number 4 are known as inhomogeneous equations, while equation 2 and equation 3, they doesn't contain charge or electric current, and hence they are known as homogeneous equations. So first we are going to utilize the homogeneous equation. We will solve these homogeneous equations. So, and the second equation which does not contains the charge, etc. So it is true for static conditions as well as time varying condition both. So we can say that in the time dependent case, the equation 2 of 5.56, divergence of B is equal to 0, still hold, and hence we can express B in terms of the vector potential. That means the vector B magnetic field can be obtained from taking the curl of vector potential A, and that way the magnetic field can be found out. Now let us understand the equation number 3. We consider the equation number 3, which does not involve any current or charges. Curl of E is equal to minus del B upon del T. This is the Faraday's law of induction. From that we have obtained these equations. Now B is a magnetic field. We can substitute B is equal to curl of A in this equations. So what happens? Curl of E is equal to minus del T of curl of A. Now del T is a differentiation with respect to time. Del is a space derivative. Del x I caret, del y j caret, del z k caret. So it is differential operator. So A is differentiated with respect to space coordinate and then with the time coordinate. You can change the order of differentiation. You can differentiate with respect to time coordinate first and then later with the space coordinate. The answer is going to be the same, and hence these equations can be written like this one. So this is equal to minus del cross del A upon del T. This side also del cross E. This side also minus del cross del A upon del T. We can take this term toward the left side. So we can write therefore del cross E plus del A upon del T, that can be written inside the bracket. This is equal to 0 because this term has brought to the left hand side. So what this means, that is curl of some bracket E plus del A upon del T, that is equal to 0. When curl of something is going to be 0, when the curl of a gradient of some scalar function is always 0, that is always vanishes. So it indicates that inside the bracket E plus del A upon del T is there, it is nothing but gradient of some arbitrary functions. We can take it. Since the curl of a scalar functions vanishes or is 0, the quantity within the bracket can be expressed as a gradient of some arbitrary functions phi or vector potential, scalar potential phi, and hence E plus del A upon del T is equal to minus grade phi can be taken. And hence we can find out from this equation that electric field E is specified as minus grade phi minus del A upon del T. So this way equation 5.61 can obtain the magnetic field B from the vector potential, and 5.63 we can obtain the electric field from the scalar potential phi as well as vector potential A. Both is required, then you can calculate the electric field. So E plus del A upon del T is equal to minus grade phi, and E is equal to minus grade phi minus del A upon del T. We have thus solved the two homogeneous equations 2 and 3 of Maxwell's equation 5.56 in terms of vector potential and scalar potential phi. Once A and phi are determined, B and E can be find out. So in some configurations, if you can find out a scalar potential phi, which is a function of R and T, and similarly if you find out a vector potential, or you can determine the vector potential A, we can determine magnetic field B as well as the electric field E can be find out because B is equal to curl of A and phi is equal to minus grade phi minus del A upon del T. We have seen in the preceding chapter that the equation 5.61 does not completely define a vector potential A. If we add the gradient of any arbitrary scalar function to the vector potential, say if A is transformed to A dash is equal to vector A plus del psi. So for a magnetostatic conditions, B is equal to curl of A was okay. But if we want to find out the electric field, which is a time varying electric field, then A cannot be completely defined. It has to be changed or it has to be transformed to some new value. So something has to be added into the original vector potential. That means whatever you are going to add, that also should be something vector quantity must be there. So psi is some arbitrary scalar function. When you apply a gradient over a scalar, it becomes vector. That means the new vector potential A dash is equal to A plus gradient of psi. Grade psi will be added to this one, and that way the new vector potential can be obtained. So if we apply this new vector potential A dash in place of A, magnetic field remains unchanged, because if you substitute this one in a equation B is equal to curl of vector A, the magnetic field will not change. How? You can see that this is equal to curl of A plus curl of gradient of scalar function, and gradient of the scalar function is always 0. So this side, this is going to be 0. So that means this remains curl of vector A only. So curl of vector A dash is equal to curl of vector A, and hence the magnetic field will not change. Magnetic field is not going to be altered. So that is important. So by this kind of transformation, the magnetic field is not going to be changed, and we can define the vector potential A dash. But now the question is this, but will E remains unchanged? In this equation we have to see that. If you substitute here, A is replaced by A dash, then electric field is certainly changed. So we have to do something that electric field should not be changed by modifying A to the A dash. So something we have to do it with a scalar potential phi also. So phi also has to be modified, or it has to be transformed to the new value of phi dash. The magnetic field remains unchanged, but will E remains unchanged? It will certainly change if some special precautions are not taken. In order that the addition of del psi should not affect the electric field, the scalar potential phi must be simultaneously transformed to phi dash. So it should be transformed phi to the phi dash, so that whatever their changes which is going to be produced because of del A upon del T, that can be compensated by these factors. And that's why this scalar potential minus del psi upon del T should be subtracted from phi, and that will be your new scalar potential phi dash will be there. In order that addition of del psi should not affect the electric field, the scalar potential phi must simultaneously be transformed to phi dash. So we have phi dash is equal to phi minus del psi upon del T. You can verify this by substituting A dash and phi dash in equation 5.63. Now, any physical law that can be expressed in terms of electromagnetic potential A and phi remains unaffected by this transformation of this type equation 5.64 and 5.65. This transformation is called a gauge transformation. Clearly, equations involving potential must be gauge invariant. So, if you are learning any physical laws related with the scalar potential and vector potential, and if the scalar potential and vector potential are transformed from old value of vector potential A to A dash, where A dash is equal to A plus del psi, and scalar potential phi is transformed to phi dash, where phi dash is equal to phi minus del psi upon del T, then the new value of the A dash and phi dash will not affect the physical laws or whatever you have studied, and this transformation is known as a gauge transformation. Clearly, this equation involving potentials, new value of the potential must be gauge invariant. In electrostatic, we adopted the condition divergence of A is equal to 0, which is called a Coulomb gauge, which together with B is equal to curl of vector A specified the vector potential. So, in electrostatic, how we specified the vector potential A? It was specified with respect to dot and cross product with the del. So, del dot A, that is equal to 0, that was a Coulomb gauge condition, and B cross del cross A is equal to the magnetic field B, and that way the vector potential A was specified. In electromagnetism, we have to make a different choice. In order to specify A, we have to impose additional condition on A in such a way that it does not change the physics. So it was good up to static conditions. That means when the electric and magnetic field are only position dependence and not time dependence, independent of time coordinates. But in electrodynamics, it is also a time dependent, and hence A and phi has to be transformed. So A is transformed to A dash and phi is transformed to phi dash, and they are going to be transform in such a way that they are not changing the physics. In other words, it must be consistent with the transformation of the equation 5.64 and 5.65 so that original electric field and magnetic field remains unaffected. In order to do this, we turn our attention to the remaining two inhomogeneous equations 1 and 4 of 5.56. So now we are going to deal with first equation and fourth equation of the Maxwell's equations. The first equation is divergence of D is equal to rho, and the fourth equation curl of H is equal to J plus del capital D upon del T. These are inhomogeneous equations because they contain charge density as well as current density, and hence we are going to deal with these two remaining equations and we'll solve them and we'll find out something from that. So we are utilizing starting with the first equation, that is the divergence of D is equal to rho. Divergence of D is equal to rho, here you can see that, and vector displacement electric field D is equal to epsilon 0 E. So that is substituted here. So divergence of D is equal to divergence of epsilon 0 E, and E we can substitute in terms of scalar potential and vector potential, which we already find out that vector field E is equal to negative gradient of potential phi minus grade phi minus del A upon del T. This is the electric field. So we have substituted in the form of scalar and vector potential the electric field, that is equal to rho. Simplifying this, del dot del is nothing but del square, Laplacian operator. So we can write this is equal to minus del square phi into epsilon 0, and this term is epsilon 0 del dot del A upon del T, that is equal to rho. Epsilon 0 can be multiplied everywhere or it can be taken as a common. So from this side you can remove that epsilon 0. So here it becomes minus del square phi, and here again I told you the del is the space derivative and del del T is the time derivative. We can interchange the order of derivative. So we can write first d dt of divergence of vector field A or vector potential A. So this is equal to minus del square phi minus del del T of divergence of vector A, that is equal to rho upon epsilon 0. This minus sign is wrong. Here no need to be minus sign. Substituting, so we can obtain the equation 5.66, which is nothing but minus del square phi minus del del T of divergence of vector A is equal to rho upon epsilon 0. Now we are going to deal with the fourth equation, that is curl of H minus del dt upon dt is equal to 0. So curl of H minus del del T upon dt is equal to Z, current density J. Now vector magnetic field B is equal to mu into H. So H can be replaced by B upon mu here, and D can be replaced by epsilon 0 E, and that is equal to J. So this equation can be reduced to like this equation, that is curl of B upon mu minus epsilon 0 del E upon del T, that is equal to current density J. 1 upon mu. Now we are substituting the value of B in terms of vector potential, that is curl of vector A. So this becomes curl of vector A minus epsilon 0 del T of E is going to be replaced by scalar and vector potential minus grade phi minus del A upon del T, that is equal to current density J. Mu is going to be multiplied everywhere. So here it is going to be removed. That means del cross factor A. Mu is going to be multiplied here. So minus mu epsilon 0 del T of minus del phi minus del A upon del T, that is equal to mu is going to be multiplied this side also. So this is going to be mu J. Now this is vector triple product A cross B cross C, and we can utilize the expansion of this one, that is a middle vector always comes with the positive sign, other vector inside the bracket is with the negative sign, and each vector coefficient is nothing but the dot product of the remaining two vectors, and it is a linear combination of these two vectors. So we can replace this one by this one, middle vector, that means del, and the coefficient is the dot product of the remaining two vectors del dot del, minus vector A into dot product of the remaining two vectors del dot del, that is going to be del square. So this identity we can utilize, del cross A is equal to gradient of divergence of vector A minus del square A, that is substituted here. So this is equal to minus del square A plus gradient of divergence of vector A. This is minus minus, it is going to be plus, and we can write plus mu epsilon 0 del T of grade phi. Again minus minus is going to be plus mu epsilon 0. This is del T, and this is also going to be del T. So it is second order differentiation, del square A upon del T square, that is equal to mu J, where we have made use of the identity this. So we have obtained the equation 5.67. Now divergence of vector A, this we have to modify. Divergence of vector A is equal to 0, which we have taken in a electrostatic conditions, but we can choose that value in electrodynamics differently, and that choice is like this, so that the original physics will not change, and this is called a Lorentz gauge conditions. We have yet to exercise our freedom of choosing the conditions to be imposed upon A. We choose vector potential A and scalar potential phi such that relations between the vector potential and scalar potential, divergence of vector A, that is equal to minus mu epsilon 0 del phi upon del T. This is the way this relations between the scalar potential and vector potential was chosen, and actually it was derived by Mr. Lorentz, that we are going to see in the next topic, that how this relations was obtained, but it is known as Lorentz gauge conditions, and this is equal to minus 1 upon c square del phi upon del T. This value of divergence of A we can substitute in this equation 5.67. What happens? Now you see that if you substitute divergence of A is equal to minus mu epsilon 0 del phi upon del T, then this equation is going to be exactly same like this equation, but with the negative sign. So the second term and third terms, they are going to be equal and with the opposite sign, so they will be cancelling out each other, and we get minus del square A plus mu epsilon 0 del square A upon del T square is equal to mu J, current density J. So we'll get this thing. We see that at once that with this substitution, the two middle terms in equation 5.67 cancels and the equation reduced to, and this minus sign, we are multiplying everywhere with the minus 1. So the first term becomes positive, del square A. The fourth term becomes negative, that is minus mu epsilon 0 del square capital A upon del T square, that is equal to minus mu J, current density J. This is equation 5.69 we obtain here. The same thing we can do with the previous result. In this result also, that is 5.66 result. Divergence of A we can substitute here. In this equation 5.66, if we substitute divergence of A is equal to minus mu epsilon 0 del phi upon del t, Lorentz gauge conditions, we can simplify it. You will see that minus del square phi minus del t of divergence of A, that is equal to minus del square phi, and this is equal to minus mu epsilon 0 del phi upon del t, that means second order derivative will be there, del square phi upon del t square, and minus minus it becomes plus. So plus mu epsilon 0 del square phi upon del t square, that is equal to rho upon epsilon 0. Now again we multiplied with the minus sign each one. So this is equal to minus del square phi minus mu epsilon 0 del square phi upon del t square, that is equal to minus rho upon epsilon 0. This is equation 5.70. If you compare the equation 5.70 and 5.69, both the equation mathematical forms are same. See here what happens. This is also plus sign, not minus, because the minus sign is going to be cancelled out here. So this becomes plus, this is going to be minus sign, this is going to be minus sign. Del square is the Laplacian operator. So it is operating on a scalar function, scalar potential phi, minus mu epsilon 0 del square phi upon del t square. That means we are taking a second order differentiation with respect to time of scalar potential, that is equal to minus rho upon epsilon 0. Rho is nothing but volume charge density. So scalar potential phi is relating with the scalar quantity rho. And in a previous equation, if you see the previous equations, del square A minus mu epsilon 0 del square A upon del t square, that is equal to minus mu g. Here also the vector potential, which is a vector quantity, we are taking operating a Laplacian operator del square over vector A. That means we are differentiating second order differentiation with the space coordinate over a vector quantity, vector potential, and we are differentiating with respect to time coordinates, del square A upon del t square. Factor is going to be the same, mu epsilon 0, and this is related with minus mu j, where j is the conduction current density, which is nothing but vector quantity is there. So mathematically 5.69 and 5.70 are having identical forms. Evidently, we have chosen our condition judiciously. The choice has yielded two independent equations, one for vector potential A, that is 5.69, and other for phi, that is 5.70. A vector potential A is connected with the conduction current density J, which is a vector quantity, and phi, which is a scalar potential with the scalar quantity charge density rho. Furthermore, both the equations have the same mathematical forms. Both potentials satisfy the same type of the equations. The condition thus introduced complete symmetry between the scalar and vector potentials. For the steady state, the time derivative vanishes, and we have, because in a steady state conditions, that vector potential A as well as the scalar potential phi are independent of the time. So the time derivative vanishes, and we can say that del square phi is equal to minus rho upon epsilon 0, and del square A is equal to minus mu conduction current density J. So this equation becomes specific in a static condition, otherwise it is a general equation related with the scalar potential as well as vector potential. The condition equation 5.68 is known as the Lorentz gauge conditions. The gauge used in magnetostatic divergence of A is equal to 0 is known as the Coulomb gauge condition. So in a magnetostatic, divergence of A is equal to 0 and del cross A is equal to magnetic field B. That way the vector potential was defined, and this is known as the Coulomb gauge conditions, and whatever we have taken now is a Lorentz case conditions which we are going to derive in the next topic. We have seen that the electric field E and magnetic field B are invariant under this transformation of 5.64 and 5.65. The potential thus transformed will have to satisfy the Lorentz gauge conditions. Hence, the gauge function psi, which so far remains arbitrary, will have to satisfy certain conditions. So, we have seen that electric field E and magnetic field B remains invariant. That means it is not changing by transforming the vector potential A to A dash, that is equal to A dash is equal to A plus del psi, and the scalar potential phi to phi dash, where phi dash is equal to phi minus del psi upon del t, where psi we have taken arbitrary scalar functions, but actually it should not be a arbitrary function, it is a particular definite function which has to satisfy the Lorentz gauge conditions. Hence, the gauge function psi, which so far remains arbitrary, will have to satisfy certain conditions. Since the original and transformed potential has to satisfy the Lorentz gauge conditions, we have to choose like this. Since the original and transformed potential have to satisfy the Lorentz conditions, that is divergence of A, that plus mu epsilon 0 del phi upon del t, that is equal to 0. This term was this side, so it is taken this side, so this becomes 0. So this is with the old vector potential and scalar potential, that is divergence of A plus mu epsilon 0 del phi upon del t is equal to 0. If you substitute new value of the vector potential and scalar potential, then what happens? That is del dot A dash plus mu epsilon 0 del phi dash upon del t, this is equal to 0. We can substitute the modified A dash in terms of the original one. So that is equal to del dot A plus del psi. This is the way this gauge transformation was done. So A was transformed to A dash, that A dash is equal to A plus del psi plus mu epsilon 0 del t of phi minus del psi upon del t, this is equal to 0. And this is equal to, by separating these terms, divergence of A plus del dot del means Laplacian operator del square psi plus mu epsilon 0 del phi upon del t minus second order derivative plus minus mu epsilon 0 del square psi upon del t square, that is equal to 0. Now, there are 4 terms, but out of this 4 terms, first and third terms, divergence of A plus mu epsilon 0 del phi upon del t, this is equal to 0. So, summation of first and third term is going to be 0, remains second and fourth term, and hence del square psi minus mu epsilon 0 del square psi upon del t square is equal to 0. Thus, the psi which we have obtained as an arbitrary scalar function, which should not be arbitrary scalar function, any functions, but it should be definite functions, which is supposed to satisfy the Laplace Lorentz gauge conditions, and that way this transformation of vector potential to A dash is equal to A plus del psi, and new value of scalar potential phi dash is equal to phi minus del psi upon del t, that way it should be chosen. Phi satisfies this equation, and hence del square psi minus mu epsilon 0 del square psi upon del t square is equal to 0. This preserves the Lorentz gauge conditions. Thank you very much, friends.